We'll start in-memory computing. That yes, memory, we know how to store data reliably, but can I use the same fabric for computing purposes, right? Which is not done today, but there is a lot of interest, a lot of motivation for doing that. So we'll talk about some of those techniques specifically for this bitwise operation, which is more like a digital computation, right? So you want to do bitwise AND, bitwise OR, bitwise NAND, NOR, XOR, XNOR, those kind of operation we'll be talking about today. Okay. So from Flash point of view, I think you have submitted homework 4. So you are quite familiar with Flash memory calculations and all. We may have another homework related to NAND, 3D NAND and others, which is more towards emerging side of memory. So after this computing topic is done, we will post that homework, okay? So let's start with computing because many of your projects topics are actually computing. So hopefully you will try to emulate something similar, how we explain some of those stuff in computing from today's class, okay? So today's class is based on these 2 papers. So one is Ambit, which is basically computing in DRAM, bulk bitwise. Another is TC Flash from my group, which is also computing inside NAND array. Okay, so these 2 papers is the base, and we'll talk more of them. So we'll have 2 parts in today's class. First part is talking about in DRAM bulk bitwise computing, and the second part will focus on in Flash bulk bitwise computing. Okay, so this is pretty much the topic I plan to cover today. Now, there is significant motivation for doing bulk bitwise operation inside memory array because bulk bitwise, bulk means it is a bulk amount of data. It can be genome sequence, right? So genome, when you sequence a human genome, it provides gigabytes of sequencing data. And if you want to do some analytics on them, right? You'll store them, say, in SSD, you will bring those data out, do some computation, bringing out and in and out will cost you a lot of data transfer or a lot of energy and latency. So can we do computation inside the SSD itself so that I don't need to bring sequencing data out, right? Those are the questions we'll be asking. So this is just one example. You can see there are many other applications where bulk bitwise computing is very much important, and it is bottlenecked by data transfer. Yes, computing in today's world, you can do in, say, picosecond range, right? In a couple of picoseconds, you can done your computing. But it is a transfer which will take nanoseconds per, say, gigabyte, right? So that is the one which is costing you in terms of computing time or energy. Now, this is your computing stack. The way we see our computing, we have CPU, we have DRAM, which is the main memory, and we have SSD, solid state drive. Now, this is the interconnect through which these 3 entities are talking with each other, right? So CPU is equipped with, say, SRAM, which is the cache memory, right? And cache size is less, right? Because it's on-chip memory, size is less, so maybe maximum gigabyte, 1 gigabyte maybe. Then DRAM will have higher density in hundreds of gigabytes, for example, and then Flash, which is in terabytes. So that's how they scale up. Now, if you have large amount of data, of course, SSD is the choice because that has highest density. It is low cost, right? To think about cost is again important metric here. But if you look at the transfer rate, right? In SRAM, you can transfer 1 terabyte per second, right? In 1 second, you can transfer 1 terabyte. That means picosecond, right? In 1 picosecond, 1 byte, or you can transfer something like that. The tera means 10 to the power around roughly. K means 10 to the power 3, mega means 10 to the power 6, giga means 10 to the power 9, tera means 10 to the power 12, right, per second. That means that many bytes you can transfer per second. So that's the speed in CPU. But you will be limited by gigabyte, this gigabyte, right? Main memory cannot cope up with this speed. And CPU is very fast. It can do computation in femtosecond, or in picosecond with femtojoule. But most of the joule will be lost in this data transfer. Here it will be nanojoule. So in one case we have femtojoule, another case nanojoule. So all those computing energy is bottlenecked by this data movement. So that's what we'll talk about, that without data movement can we do computation. So this is how it will be done. So now this is one wall is memory wall, which is the main memory and CPU bottleneck, which is 50 gigabytes per second in today's DDR5 interface. If you look at storage side, this wall is even bigger because there your transfer speed is very small. It is in the order of, I think 10 gigabyte per second in that range with PCIe bus and all. Okay. So these are the two walls, and today's class we'll see how to breach this wall, right? So can I do computing inside this memory chip so that you can reduce this memory burden, right? So there are some proposals in literature, if you look at, they try to embed a processor inside the SSD. If you look, so this is the entire SSD. So SSD composes of several NAND memory chips. It also has a processor. Now, if you do computing inside the processor, you may say, okay, I'm not transferring the data outside the SSD. But again, you will be limited by this internal bandwidth of SSD, because data resides only in the memory chip. You have to bring those data to the computing processor. So that means you are just transferring the wall from outside SSD to inside SSD. So that's where traditional in-storage computing proposals are. But the best way is if you can do computing inside this chip, right? So that you can directly transfer the data or computation result, then you are breaking the memory wall, basically. So that's what the topic of today's class, that can I do computing inside this memory chip, not just inside SSD. Question on this big picture. Okay, so the bottom line, what I would like to say is this data movement, right? From memory means this main memory to processor is one bottleneck, which is called memory wall. Then data movement from the storage, which is the SSDs, for example, predominantly. So that movement will also cost, this is called storage wall. So how to break those walls, right? Or how to bring computation inside the array itself. That is the goal for today's class. So with that goal, let's start with DRAM first, and then we'll talk about flash. So just quickly recall, this is how your DRAM array looks like. It has row decoder, which will select a particular row, right? And this column decoder, where this particular column address will be selected, or this data, right? This is the bitline direction, vertical. So data from this row will come to this data buffer through a sense amplifier. So sense amplifier will sense when you activate the bitline. Based on the data, bitline voltage will go up or down, and then sense amplifier will amplify that. Or more clearly, I think this is the picture in this course you have seen when you talked about DRAM. This is a DRAM cell. It is 1T, 1C. This is the capacitor. This is the access transistor, right? This is the capacitor. This is the DRAM cell. It is connected to a bitline, and bitline is connected to a sense amplifier. Okay, so during sensing, you will precharge this bitline to VDD by 2. Now, based on whether the capacitor is charged or discharged, after sensing, the bitline voltage will go up or go down. And that's how you sense, right? Then sense amplifier will amplify that little bit difference, and it will raise the bitline either to VDD or ground. So you start with middle way, VDD by 2. And then based on the data, the data will be sensed. And then it will be right back on the same capacitor, because DRAM read is a destructive read, if you recall. So this is a few things you need to keep in mind. I'm recalling it because when you do computation, we should not destroy our operands, right? Because we have operands stored in the memory. We'll do the computation, we'll transfer the results, but operands should not be destroyed. So that's another important criteria that you need to keep in mind, how to do computation without destroying the data. And first of all, let's ask how we'll do this computation using this machinery, because we are not changing the hardware. Without changing the hardware, right? Suppose I have a commodity DRAM array. How can I do computation inside this array without this changing the hardware? Any question here on DRAM operation? It has been some time. Okay, so now let's look at how we'll do the computation. So let's go one by one, okay? So, or before going computation, this is important to understand because this is what we'll be using for computing as well. So for the state transition, right, during sensing. So you start with this pre-charged state. So this is the step number 1 when you read data from an array. So I'm showing only one cell, but you understand that this cell, there is parallelly in a given row, there are 4K byte, for example, is connected in one row. Okay, so this is your one row. Row voltage is 0 because it is not yet activated. The red color you see in the, that is means it is activated, right? So first is just you pre-charged this bit line. Bit line is ready for sensing, half VDD, right? Row is not yet activated. And this is your sense amplifier, which will amplify the bit line voltage, whether it is plus or minus, right? So, and sense amplifier output will be given to the data buffer and all. So this is your first step. Then you start activate. Activate means you turn on the word line. Now the word line will talk with this capacitor, or this switch is closed basically. This access transistor is act like a switch. The moment you activate, switch is closed. Now this capacitor and this bit line will talk with each other. What do you mean by talking? What is that technical term? Charge sharing. So they will share the charge, right? Because when the moment you close this switch, this capacitor is, for example, in this case, charged. You can see full. So now bitline is also has a capacitance, bitline capacitance BBL. So they will share charge among each other, and at the end of the day, both capacitor and the bitline will reach at the same voltage. So at the beginning, what is the voltage? Bitline is half VDD and capacitor is VDD, fully charged. After end of sensing, both will be VDD plus delta. So delta is the extra voltage, right? If delta is positive, the sense amplifier is not yet activated. We are in step 3 right now. Step 2 is just activation of word line, charge sharing is taking place. At the end of this step 2, charge sharing has already taken place. You are at a state where bitline voltage has been changed, and both bitline voltage and the capacitor will come at the same voltage because they are parallel capacitor. Okay, so they are in the same voltage now. Now, if the bitline voltage is increased, now then the sense amplifier will activate it. So you activate the sense amplifier. See, initially sense amplifier 0 means it is not enabled, disabled, right? So now you enable this in step 4. You enable this sense amplifier. Sensing will raise the voltage, this VDD by 2, right, in other bitline bar, and this is VDD by 2 plus delta. So this change in voltage will force the sense amplifier, when it is activated, will force it to VDD, the full rail voltage, right? Half VDD will go to VDD and this will go to 0 because this is a little bit extra high. And then you activate this word line, or word line is activated, so this cell which lost its charge during sensing will again be written back. So that's the whole sequence of steps when you read the content of the memory. So far we are not doing computing yet. We are recalling or revising our sensing mechanism, because that is the whole point, right, for computing as well, that will show in the coming slides. And one important metric here is this delta. And this delta depends on this capacitance ratio. The cell capacitance CS is the cell capacitance, this capacitance, which is small, and C bit line, which is maybe 10 times, at least 10 times or 100 times higher than the cell capacitance. So that means here numerator is small, denominator is large. So a very small delta will be created. Okay, and if VDD is 1 volt, this 0.5 times this point diffraction. So around 50 millivolt difference you create basically. So that's the whole process. After sensing is done, you again pre-charge the bit line and you wait for next cycle of sensing. Any question on this process of how you sense? And this process will be parallelized, right? Because this is bit line, one bit line is one cell, but there are thousands bit line in parallel working for you. So in one cycle, you know all the state of the 1,000 cells. Okay, so now if this process is clear, now let's do the same process with little bit addition or little bit change for computing. So this is how in DRAM computing will take place. So you have to activate multiple row together. So in this case, the paper ambit, they talked about triple row activation, and three rows are activated simultaneously. For normal read, you activate one row, right? One row at a time. But suppose here A, B, and C, and you want to do say AND operation between them, or you want to do OR operation between them, right? So what will be the AND operation result for A, B, and C?
Zero.
It should be 0, right? And then we'll see whether it will be 0 or not. So that 0 should come here, right? That on the right now bit line is half VDD. If it becomes 0, then here 0 volt should come in. If it is OR operation, what should be the voltage? Should be 1. So then it should go to VDD. So that AND or OR operation determined between A and B, it will be determined by C. That's why C is used, 3 row. So C will decide whether you want to do AND or you want to do OR, right? So we'll talk about it. So if you put C equal to 0, for example, you will do AND operation. If you do C equal to 1, for example, you will do OR operation between A and B. But let's first understand this triple row activation first. This is the setup, right? This is just for one bit. For simplicity, we are just showing for one bit, but this will be parallelized on the entire row. Questions? Anything that makes sense? This is the initial setup, right? So you have data on A, B, and C. These are the 3 rows, 3 bits on 3 different rows, and we will be simultaneously activating them. So these 3 rows are closed. This is the access transistor. So all the 3 access transistors are closed right now. What is going to happen? What will be the bit line, final bit line voltage after this? So there will be charge sharing taking place. So what will be the final one?
VDD, correct?
So will it be more than, because some charge from these 2 will come to C as well. So overall, will it be half VDD plus delta or half VDD minus delta? Plus delta. Suppose it was only one, A is only charged, B and C are empty. What will be the? It will be minus delta. So that's the important thing. Okay. So it's more like a majority vote. If majority of the cells are charged, you will get plus delta. If minority cells are charged, minority means either none of them are charged or one of them is charged, you will get negative PT. So that's what is going to happen, right? By simple logic. Does it make sense? We can exactly calculate what will be delta, and we'll show it in a couple of slides, but let's understand the computation operation. So you are simultaneously activating all 3 rows, and then what is going to happen? There will be charge sharing taking place, right? This full capacitor will discharge, and all this capacitor will come to the same voltage, because this is the whole point, right? Charge sharing means after charge sharing, all the capacitor will come to the same voltage, because they're in parallel. Okay, and then you'll get a delta plus delta here, because you start with 2 cells being fully charged. Because it is delta, your answer will be 1, because now the sense amplifier, right? One other end of this amplifier is fixed, which is half VDD, always fixed. So if your bit line, sensing bit line is a little bit more than half VDD, sense amplifier will make it 1, right? So next step will be, it will be VDD and this will be 0. So you are getting your output result as 1. So that is the whole point of computing, that you have to do multi-word line sensing, or you have to do multi-row activation. And the operation you are getting, and then after that you will, of course, get the results. You can read any of this row, you will get the result. Because all 3 rows after sensing will come to the same value. Right, so because this is 1 bit. For another bit, it could have been 0. Another bit, it could be 1. So your results will be stored in the word line. Okay, so final state of the bit line will be VDD if at least two of the cells are 1. So how mathematically you can write this logic using ABC? So you found a logic, right? If majority of the bits are 1, then your final result is 1. If all three are 1, yes, final result is 1. If 2 are 1, yes, final result is 1. If out of 3 cells, if 1 is 1, it is still 0. So what is the logic? Yes.
Depends on C's charge or not.
Yeah, I mean, including C. So C is also a variable, for example. So how will mathematically write this logic? So it's a majority function, right? Which is AB plus BC plus AC. If all three are 1, yes, output is 1. If any two is 1, output is 1. If only one of them is 1, output is 0. Right? Which you can write. So this is the final state, AB plus BC plus AC. This is the logic that we talked about. If there is a doubt, let me know. But this is a majority function. And then you can rewrite this logic as C times A plus B, C bar times AB. Now you can see, right, you can do, if you want to do bitwise operation between 2 bit, A and B, then you can take C as the control point. You can make C equal to 0, right? Then this is gone. Then this will be AB. Then you are doing AND operation. Right? So if you do C equal to 0, for example, then it will implement bitwise AND between first two row. If you choose C, right, that row is 1, then you will be implementing bitwise OR. So that's the logic for doing in-memory computing. One row, you will be initialize all 1 or all 0, depending on which operation you want to implement. And the other two row will have your operands. Yes?
Sorry, so to read out the final state, that's A and B, or B and C, or A
So C, right, C row, third row will be either all 1 or all 0. All 0 means you have thousands of bits in parallel, right? This is one of these 1000 bits. So if this is 1, then your final result is A plus B, because this C bar will be 0 in that case.
In this case, so A plus B is equivalent to A or B.
A or B, yeah. If C is 0, then this is gone, then it will be AB. So this is bitwise operation, logic. Yeah, so that's how this ambit paper implemented the logic. Any question on this implementation of logic? Okay, so this is, you can extend it, but this is just the core of the logic. Now, if you want to do some math, okay, what is my delta, right? So you start with half VDD. Suppose two of them, in this case, B and C, are fully charged. After, this is the activation, triple row activation. This is the key. In normal read, in normal DRAM read, you never do triple row, right? You just do one row by one row. You read one row by one row, right? But this is for computing. If you want to use the same fabric for computing, you have to do multi-row activation. So that's one change. So if the moment you do this triple row computation, triple row activation for this scenario, you get plus delta. Can anyone tell me what will be the value of delta? Or how you will compute this value of delta?
Isn't like 1/6 VDD?
1/6?
Yeah, VDD, because it shares it between everything. So each capacitor is 2/3 VDD.
So 1/6 VDD will be the case if I think all three are discharged. Because there will be some charge, right, at the beginning.
If 2 are charged.
Huh? Yeah, only 2 are charged. Yeah, so let's say, I think maybe you are close. You're not exact, but very close. So let's see how we will do this. So this is your general philosophy that we read. We also did it for normal sensing, right? When you do normal DRAM sensing or single row sensing, we started with this criteria because charge is conserved, right? Charge is a conserved quantity. So before sensing, whatever your initial charge was, after sensing, the same charge, total charge will be the same. So what is before sensing? This is your before sensing charge. So charge is on bitline capacitance, charge is on the 3 capacitor, right? Capacitor charge is QCV, right? Q equal to CV. So capacitance, cell capacitance times voltage, VDD. What is charge on the bitline? CBL, bitline capacitance times half VDD. So that is your initial charge. K here stands for the cell, number of cells which are in the fully charged state. If K is 0, none of them is charged. And then in that case, I think you will get 1/6 VDD. But yeah, so this point makes sense, right? You can generalize because there will be maybe homework problem coming up. on some of those calculations. So before sensing, based on number of cells being recharged, so number of cells holding 1. So K is the number of cells holding 1. In this case, what is the value of K? 2, right? Because 2 of the cells are 1, right? Just to check whether you are still awake. Yeah, so two cells are 1, so K equal to 2 in this case, and then you get this, but in general, you can write it like this. And then in the final stage, what is your equation? Final stage, everybody is at the same voltage because we are in parallel. All 3 capacitors has to be in the same voltage with the bit line. So this is the final voltage, which is the half VDD plus delta, right? All this bit line and this cell capacitor will be same voltage, and this is the total capacitance. Total capacitance is 3 CS because there are 3 cells we are talking about, ABC, and the bit line. So now we can find what is delta. So this will be the equation for delta. So if K equal to 0, right? You can see this terms goes away, then you will get, no, it is not 1/6 actually, still. 3 divided by 6 plus 2BL. Yeah, it's not exact, but if you, so this is an exact expression. So you can plug it in and see what value you will get after charge sharing. Yeah, now 1/6 VDD is very large, right? It will not be. Delta is very small. Delta is millivolt. VDD is in 1 volt. So 1/6 VDD will be very, very large voltage. It will never happen. Yeah. Because it's not just voltage, right? It's the charge that is shared. And charge depends on capacitance times voltage. So since these capacitors are very, very small, cell capacitance, bit line capacitance is very, very large. So yeah, so that's why this expression will give you the exact quantity of voltage rise or low. Now you can see, right? This, if delta should be positive, that means 2K plus minus 3 should be positive. That means K should be more than 1.5. That means K is the number of cells. That means K has to be 2 or 3. So only then it will go to VDD. If delta is positive, bit line will go to VDD. If delta is negative, bit line will go to 0. And that will happen if majority of the cells are charged. So this is the framework for computing. Any question on this framework? You can exactly find delta and everything using these expressions. Now, how will implement? What is the drawbacks of this framework? If you want to do computing using this triple row activation, what is the problem?
What is the problem?
Well, I mean, your computation will not be always correct because this depends on delta, right? Suppose these cells will be discharging, right? Because DRAM is a dynamic memory. Capacitors are always discharging. If they're not fully charged and you do computation after some time, you can come up with a wrong result. Because delta is anyway small, and here it will be even smaller because of all those charge sharing. One problem. Problem number 2, your data is lost, right? Because after sensing, everything will be A, B, and C. All 3 rows are having the same results. This is another problem. Huh?
You're getting rid of your operand.
Yeah, your operands are destroyed. That is also not desirable. So how will do this? How will solve this? That's where this paper comes in. So you should explain like this, right? So you tell what is the problem and then come the paper. This paper is about this, how to solve those kind of problems. So they acknowledge those problems. One is there is a weak sensing signal because after charge sharing, delta can be very small, right? It is not, say, 50 millivolt, it can be 10 millivolt or low. Process variation, not all cells will have the same capacitance, some difference in capacitance. That can also cause erroneous result. Data is destructed. Data destruction means in the operand. Operand data is destructed, which is not desired. And charge leakage always takes place. So depends at what time you're doing computation, right? During that time, if there is a lot of leakage has already taken place, your computation result may be wrong. So all those things are, and then there is a hardware cost as well because you have to do triple row activation instead of single row activation. So some modification in hardware is also needed. It is not like you have to add maybe a little bit different types of decoder, right, which will do this triple row activation. So these are the problems. Now the way this paper solved this problem is as follows. So this is the implementation of Ambit. So they says that, okay, all this computation will be done in 3 reserved row. So there will be 3 reserved row. So reserves a set of designated row, right, in each subarray. To perform bitwise operation, right, first they'll copy the operands into those designated rows. So that means your operands are not destroyed, right? So these are the 5 steps they propose. Copy data of row A to a designated row, say T0. This is your computing row. This is your data row, usual data row. Then copy data from row B to another row T1 and initialize the designated row T2 with 0, right? So 0 means which operation you'll be doing. So if you initialize, it will be AND. I mean, if you initialize it all 0, it will be AND operation. If you initialize it 1, it will be OR operation. And then they will activate all three rows simultaneously, and you will get the results in any of this row actually. Because this row doesn't matter. Your original data is already there in A and B. Okay, so that's how their proposal is. But what is the innovation in their proposal? One is, of course, we understood this multi-row activation. This is one innovation, which is not done in normal DRAM chip. Another innovation is copying from one row to another row. That is also not done in today's world, right? So this need a technique to efficiently copy data between rows. So these are the 2 main key innovation in that world. So how copying is done in today's world? Suppose you want to copy this white row to a dark row like this. You know how it is done in today's computing stack? So first you will get this data byte by byte to the CPU. Yeah, that's how it is. In today, there is no way you can copy from one row to another row in a DRAM. You take the data to the CPU, write it back. It's a huge bottleneck. Then all this computation benefit will be gone if you do this like this. Right? So this is how today it will do. And then you'll copy that, right? So now what is the problem? One is you have long latency to read byte by byte or word by word. Then high bandwidth, you have to use this bandwidth, data transfer bandwidth, right? Because you have to move the data. Your cache is getting polluted because polluted means it is getting occupied, right? With more data transfer. And then unwanted data movement will take place. So all these things can take in thousands of nanoseconds, which is microsecond, right? So your computing is limited by bottleneck of data movement. You can see that. Now, what this paper says, okay, I can do copying, right? If you ask a 10 years old, how will you to copy this white to black? They'll not transfer the data to the CPU and all. They'll say, I'll take it from here to here. And that's what it should be, right? If you just copy from here to here, data is copied, but there is no way right now on DRAM you can do this. So, but if you can do this, if you can directly copy from one row to another row, you will increase latency, or you'll decrease the latency or increase the performance. You don't need to utilize bandwidth, or bandwidth utilization is low. No cache pollution, cache remains as it is. No unwanted data movement, right? So that's the thing, and you can do this in 90 nanoseconds because from one row to another row, you don't need that many nanoseconds. Now, how to do that? So this is how you'll do it. So you first, step 1, you activate the row which you want to copy. So this is your source row. So you activate it. The moment you activate, data comes to the buffer, right? So data will come from this row to the buffer. So you're not transferring data out of the chip. Data is inside the row buffer. Next, you will activate the other row and then write it back. Because data buffer is common for everybody. So you're copying from one row, bringing in the data to the data buffer, and then write it back on a different row. So you basically, 2 simultaneous activation is needed without transferring the data. First you row the source row, then you activate this destination row, and from the buffer, data will be transferred to the destination row. So that's what the other idea of this paper, row cloning. How to clone one row to another row with 2 consecutive activation command. With that, they solve most of this problem. Most of this problem means, yes, question, yes.
Yes, so DRAM, the read is destructive, correct?
Hmm.
And we have this process of rewriting whatever gets into the buffer back into the memory location.
Yeah.
When you activate row B
Mhm.
to rewrite, do you ever run the risk of there being a value there that gets essentially injected into the previous value because of a
No.
I guess are you reading when you activate B2 row B?
No. So this data is already there in the row buffer, right? So if you recall the 5 steps of, that's why we state initially, right? That when you pre-charge the bitline is BDD by 2. That means row buffer doesn't know whether it is 0 or 1.
Yeah.
Only after sense amplifier is activated, row buffer knows what is the data.
Okay.
So when you, for example here, step 1, right? When you activate row A, that time charge sharing will take place. And after that, row buffer data will be automatically written in the row A. So row A is not losing data,
Okay.
right? And this content of row A has now faithfully came to the row buffer because sense amplifier is activated. So now it is not read operation. Second activation is not read operation. Second activation is write operation.
So is there a possibility of adding data to the
No, because it is digital, zeros and ones, right? So no matter what is the state of row B, whatever data is in the row buffer will be written to row B. So first step is read operation, right? So after read operation, row A is written back, so row A is done. You deactivate it. Now second process is step 2, which is the write operation. So write operation means you can do overwrite. If it is 0, you write 0, no problem. If it is 0 and you have to write, then charge will go in, and then sense amplifier will again kick that in. Okay, so I think just look at the write operation of DRAM. So second step is the write operation. I understand your confusion because you are talking, okay, I have some data already. If I write it back, will there be any problem because of my previous data on row B? Answer is no. Okay, so that's their other steps. And if you want to see this, how row cloning happen on a single cell by cell basis, right? Suppose a cell, source cell is charged and destination cell is discharged, suppose. In this case, this is your VDD, this is VDD by 2 bit line, this is the bit line, this is the access transistor. What you will do first, you will sense source, right? So that's why you close this activate this source word line. When you activate the source word line, this VDD by 2 plus delta will come in, right? Charge sharing is taking place. And then you amplify this difference using the sense amplifier. So first you activate the source row, then you activate the sense amplifier, and then sense amplifier will amplify this voltage difference. Then this voltage difference will go into the source. The source will get back its result. Oops, sorry. Right, so this is the source will get back to its original state, and then you deactivate the source. So you're deactivating the source. So source data is preserved. Now it is coming up a write operation on destination, and write data is already in the bit line. You close these things. The access transistor. If this bit line is charged, it will charge this capacitor, and that because it is high capacitance, right? So it will not lose charge in that process, right? So this bit line will be, or this destination side will be charged. So this is how the copying happens. If it was already charged, then nothing will happen in that case. So as we are saying, that charge will not go up because charge is determined by level, voltage level. It will not go beyond VDD. It will remain VDD. Yeah. So that's the thing. So data gets copied on a destination row, and you are done with your computing without transferring the data, without destroying the original copies. So copying is a very important part of their proposal. Okay, so yeah, so this is the key aspects, right? When you present computing work, you need to focus on the fundamental mechanism, machinery, and what are the drawbacks. So that's what we expect from different computing presentation. Any question here? So it is done, MBIT paper is done. This is the whole point. And then they have done a lot of evaluation on different hardware and all. So yeah, so I think I'll move on to the next topic, which is the in-flash, right? We understood how we do computation, bitwise computation inside DRAM, using multi-row activation, using row copying. These are the two main mechanisms. Now let's look at how in-flash computing can be done. Same bitwise operation in the flash memory. I hope with the background that we have so far, right, in SRAM, DRAM, and flash, right, we know cell, we know array. These computing things make sense to all of you. You are liking this aspect. These are new stuff. And these are very important for AI or data-intensive workload, right? Because all those machine learning, AI, right, they are depending on huge volume of data. Data movement is the real bottleneck. That's why you see NVIDIA is hungry for high bandwidth memory. HBM, all these memory companies' stocks are 10 times higher because of this AI workload need. You need more memory. Everybody is producing more and more memory to feed in this AI workload. So data transfer bottleneck is still not solved. These are the techniques, right? This is where industry is thinking about how to minimize this power and latency for AI workloads. Let's look at bitwise operation. So one paper was there from actually same group. This Onur Mutlu, he's from ETH Zurich. So they had a paper on, the Ambit paper is also from their group. So they also had a paper on in-flash bulk bitwise operation. And it's very similar like Ambit, and I'll talk that first and then finally I'll conclude with our group's work. So their proposal is like this. So you have a flash memory block, right? All the operands are in word line. Remember flash memory block, how does it look like? There are multiple word lines. That's what a block is formed. And those word lines are series connected cell, unlike DRAM. So that's inherently you can get computing using that. So their paper name is Flash Cosmos. That's what they named the paper. And in that paper, they talked about, okay, you populate those word line with the operand, and then you do simultaneous activation, right? When we read NAND array, right? We read one word line. What about the other word line? They're in the pass state, high voltage state, so that no matter what is the content, all these cells are closed, right? If you recall, right? Let me very quickly go out here. In the last class we talked about, right, this pass, disturb, and all. So you see, this is your one, your another one. So this is how your word lines are, and then this is the second word line. This is your second word line. This is your third word line. Right? So when you read this cell, this voltage will be V pass. This will be V pass. And this will be V read or reference. You're going to read this cell, you will put all the other cells in the pass mode. Pass voltage will be high, say 8 volt. Right? V reference can be low voltage, 0 volt, 1 volt. So you want to see whether this cell is conducting or not. You have to make sure that all the other cells are conducting. But this is called single word line. But if you want to do computation in this framework, you have to make this is also VREF, this is also VREF, this is also VREF. If you do, instead of pass mode, if you put them in the reference mode, multiple row, then if all the cells are erased, only then current will flow. Right? All the cells are erased means their cell voltage is low. If all of them low, only then current will flow, which is which operation, AND or OR? AND operation. Erase means logic 1, right? If all the cells are erased, logic 1. Suppose this is storing 1, this is storing 1, this is storing 1, right? Then if you put VREF here, it will do 0 volt VREF. Erase voltage is a negative. Or say maybe 1 volt, 1 volt, 1 volt. This is the minimum reference. Erase cell with a threshold voltage is low. So you don't need pass. Automatically, all the transistors will conduct, you get 1. If any of the cells is programmed, there will not be any current. Right? Suppose this is storing 0, or any of this is storing 0, there will not be any current. Right? So then it is 0. So that's how you see which string is conducting, which string is not conducting. Simultaneously, you can do AND operation. Questions? Okay, so that's their proposal. So you can see they're saying 0 means switch is open, 1 means switch is closed, right? So if you do, if all the switches are closed, only then current will flow. If any of the switch is open, current will not flow. This is called multi-word line sensing. Yes?
Does this still work for like multi-level cells?
That's a good question. So this is only for single level cell. this proposal was. But we'll coming there. I'll be answering this. Okay. Any thoughts? So here every cell is just storing one bit, either 0 or 1. This is their proposal in their Flash Cosmos paper. But what are the drawbacks in this paper? So yes, theoretically you can do it, right? This process. Theoretically, Ambit, Flash Cosmos, you can implement on the same hardware. But practically you cannot, because if you look at any chip, they will never allow you multi-word line sensing. You sense only one word line. That's the process, right? How you read memory. Reading memory is word line by word line. So multi-word line sensing is theoretically possible, but practically not, at least not on the existing hardware. Second, if you look at here, right? Your resistance, when you do pass, right? These are fully on. Our drag voltage is very, very large. They are fully on. You're not adding up resistances. But when you do multi-word line sensing, all these resistances will come in. So your sensing current will become very, very low. So yes, theoretically again possible, but if you look at practically, multi-word line sensing in NAND is very hard because NAND already is long stack, right? Long word lines. So you already have low current, yes.
Is it predicated on measuring like a delta?
Just like in Bitline, we have delta. Here is more like current. How much current is flowing? So yes, you can say, okay, all these cells are on. Because this is 1. So if I put here 1, our drag voltage is suppose 1 volt. But still, there will be some resistances, and all those resistances will add up, right? And your sensing current will go to the sensing limit. So again, theoretically possible, but practically harder to demonstrate. Okay, so same thing you can do for OR operation. For OR operation, you have to do multi-block sensing, which is again not a standard mode. So you have one operand in one block, say block 1, another operand in block 2, and then they are sharing the same bit line. Because bit line goes from one array to another block 2. All the blocks, they share this common bit line. The bit lines are big, right? We talked about. So between two, so word line, whichever, if any of this is on, bit line will discharge basically. So, so that's why they'll do this multi-word line sensing for bit line or multi-block sensing, basically multi-block sensing for computing OR operation, because any of those block which will be in the conducting stage will discharge the bit line, no matter others. So that means it is OR operation. So for AND operation, it has to be intra-block. In a block, you will do multiple word line sensing. For OR operation, you will do multi-word line and multi-block sensing together. So that's again a lot of power because you have a power limitation. Every block is ginormous, right? In NAND. NAND array is large. Block size is very large. If you activate multiple blocks together, this is the problem again. So yes, this paper is good, but it has some drawbacks. And that's where I think we started our research, and that's where I'll answer to your question, multi-level cell. We utilize this multi-level cell, and we propose this work that we can do bulk bitwise processing without multi-word line sensing, using single word line sensing, which is the commodity mode, which is the default mode, right? So in this mode, can I do computation? So let me explain some of those parts, and that's where this multi-level cells comes into picture. Because in NAND, one word line, right, can store 2 separate pages, because one bit can store, say, 2 bits, which is the multi-level cell concept. And those 2 bits are independent. I mean, you can have 2 logical pages, 2 completely random pages mapped into NAND array. That's how you write in a multi-level cell. For example, if you want to write 1, 0, 0, 1, 0, 0, this kind of things, you just take this 2 page of data and you decide this cell will go to the which state, this cell will go to the which state based on multi-level encoding. For example, this cell will go to the which state, the first one. If both are 1. If both are 1, it is the erased state, lowest bit state, right? So that's how we will do this encoding. So this is the mapping of data. So now I can choose what voltage, threshold voltage, this cell will go. This cell will go to the lowest threshold voltage because it is 1, 1. It is 0, 1. So it is the next step, next threshold voltage steps, 2 volt. This is the 4 volt, which is the threshold voltage of this third transistor will be 4 volt, and threshold voltage of the fourth transistor will be 6 volt, and so on. So you can map the user data, which is randomized data, in the MSB page and LSB page, and you write it on the array. So this is a write part, a normal write, right? So now you have this, and during write, we talked about ISPP, incremental step pulse programming. So that's how you make sure that how many electrons will be injected, what threshold voltage this will go. And that's the process of writing the 2 page of data on a same word line. But this is not computing yet. This is the normal operation when you write. Now suppose I want to do computing between these bits. What should I do? This is the question. So computing will be done just through read, right? You saw, right? Either multi-row activation read or multi-word line activation read or single word line activation read. So here you have to do single word line activation read where there is a default de facto mode for any memory chip. So this is the way you will do the computation. So for normal read, first to understand normal read, and then you will understand computing read. For normal read, how will read? For say LSB page. Suppose you want to read the LSB page. So for LSB page, these 2 bits are 1, these 3 bits are 0, right? So how we will read it? Where you will apply your read reference? You have homework 4, right? You have some question on that. Around 3 volt. That's the correct answer. So you just put reference 3 volt, then automatically these 2 bit will conduct, even though it is programmed at 2 volt, even though it is 0, no matter, right? Both of them will conduct, these 2 will not conduct. So you get your results. Now question is, if you want to do AND operation, right? This is not your AND operation. This is the original data. You get your original data. If you want to do AND operation, how will you read it? For AND operation, only this L0 should be 1. Everything else should be 0. Cells only in the both bits are 1. Only that should be 1. That means instead of putting reference at 3 volt, if you put it at 1 volt and read the same page, you get the AND result. So that's the idea. So for example, let's see. Yeah, so this is just to show how you will read MSB page. For MSB page, you have to use 2 reference. You put here, and that's how you can get MSB page results. So LSB page is simple. You just read 1 reference, see whether you are in L0 and L1. If you are in L0 and L1, you get 1. If you're in L2 and L3, you get 0. But for AND operation, you just change this reference here. And then you do the same read, you get the AND result. And similarly, you can do other shift for getting OR, XOR, XNOR, anything using this framework, which I'll show. But I hope this reminds you, right, how we, because this slide was not for computing. This slide was just to show how we read in MLC. We read MLC through this applying reference. So 2 independent logical pages share the same physical word line. And that is the mechanism we exploit. That, okay, you have 2 independent pages, which can be your operand, 2 independent operand. And since single word line sensing is possible, since reference shifting is possible on a commodity chip, so you can demonstrate on a commodity chip without any hardware modification. So that's the idea. So let's look at this AND operation. So we talked about, we already answered this question, right? So for AND, only L0 should be 1, because this is 1, 1, right? This bit. This distribution means a particular bit, particular cell, lowest threshold voltage. L1, L2, L3, these are other threshold voltage. So all these cells which are parallelly connected in a row, we are combining them into 4 groups based on their threshold voltage, right? Now when you apply word line voltage, which is this, you get the LSB data. But for AND operation, all you need to do, you need to correct this. Because if you just read LSB data, this will be wrong. Here 1 is 0, 1 is 1, but you are reading it as 1. So for that, you need to just shift the reference like this, which is nothing but you can easily do it on a single word line sensing. And that is allowed mode. If you do that, then you get results 1, 0, 0, 0 from the LSB page. So you have to read the LSB page with shifted read. That is the mechanism. Okay, so this is your result, A and B, and result will come in the buffer. Your original data is not destroyed because this is a read operation. You're not changing the original content. If you want to get back your original content, you bring back your original reference and read that again. Question, anything? Okay, so that's the logical AND. How will do logical OR? Suppose you want to do OR, right? So A and B, these are the 2 operand. For OR, only this one should be 0. Everything else should be 1. So how we will shift your reference? So here you have to read MSB page. With LSB page you cannot read OR, because if LSB page, yeah, these are 1, these are 1, you cannot make this is 0 and this is 1. But with MSB page you can do it. So this is how you can do it. So for MSB, this is the two reference, VREF0 and VREF2. So if you just read MSB page, yeah, this will be 1, this will be 0, which is wrong, this will be 0, which is correct, this will be 1, this is correct, right? This is the MSB page data, if you just read with default reference. But if you shift this reference here, then this bit will become 1. And with this shifted read, if you read the MSB page, you get your OR result. So that's how it is, just playing with where the reference shift, and that is you can do on a commodity chip. In a commodity chip, you can shift the reference with some command, right? So you can do without any hardware modification, without any command change, computing using single word line sensing. You don't need multi-word line sensing to do computation. Okay, so these are the steps, exact command, which is called read retry, which will shift the reference. So we can do computation. Any question here so far? How to do AND and OR? Now, good news is you can scale it up, because this is not just 2 operand. You can do it more, because NAND, right? We know MLC stores 2 logical pages, 2 bits. If you go to TLC, you can store 3 bits. That means you can do operation on 3 bits together. Or you can do 4 bits, because QLC is also commercialized. You can do on 4 operand together. So you can scale up the computation efficiency using logical scaling. So that's another advantage, because you can see, right, just for AND, all you need is L0 should be 1. First step, where all the bits are 1. Everything else should be 0. That means you just shift the reference here and just one sensing, done. So your computation result is ready. Okay, so we did all those computation on commercial chips. For example, these are the flash chips. We interface them and we send read command. We shift the reference and say read, and we get the results. So these are results, and we found that 0 RBR for many operation, as long as the flash is fresh, right? We talked about fresh. Flash memory has reliability concern, like endurance, has a finite endurance. Endurance means if you use more and more, the distribution becomes wider, and then you can see some error. These are measured result on real chips, how these operations perform under bitwise operations. So yes, on a cycle means worn out memory, you see some error, but on fresh, we don't see any errors. Now, we can also quantify the energy efficiency of all these operations. So energy efficiency you can quantify if you measure current, right? Your supply voltage is fixed, 3.3 volt, for example, on a chip. But you can measure during your operation, right, when read is happening, what is the current consumption. So we did this, so we can see as you increase this QLC, MLC, TLC, QLC, right, you can improve the performance because you are doing more bit operations together, right, in QLC, but at the price of increasing energy, because you have to apply more references, right, to decode. And so yes, so logical scaling will improve the performance of your bitwise computation, but it will also make it more energy consuming stuff. Right? This orange is the current consumption when you're reading a QLC memory chip, which is high, 1.1 nanojoule compared to MLC is 0.3 nanojoule. Right? So which memory you should choose for computation depends on what is the optimal point. Right? So that's why you chose that. Okay, if you choose MLC, this is my performance and this is my energy efficiency. Energy efficiency is with dark color, performance with light color. So as you can see, performance will increase because you are doing multiple operations together as you go for QLC or maybe PLC in future. But at the same time, your energy efficiency will fall down. So it looks like TLC gives you better compromise, a better trade-off. So that's the stuff we did. Yeah, so I think we did a lot of other evaluation that why there is some RBR, because NAND flash has raw bit error issue, right? When you sense some, because the distributions can overlap with each other, there's less margin. Because these are not meant for computing. These chips are meant for storage, right? You always use error correction code, but for computing, you cannot use error correction code. So that's why you can see some RBR and all. So yeah, this is, my student is working on how to make it 0 RBR and other things on this topic. Okay, so I'll just skip some of those things. So these are just to tell you how much shift depends on what is the RBR. When you shift the reference, if you're not shifting it appropriately, right, then there can be some RBR, but if you shift it appropriately, then RBR can be made 0. So there are some of those things analysis we did, but this is where I'll stop now. One of the challenge in this approach is both the operand has to be on the same word line. How to do that, right? Because suppose in a memory, your operand 1 in say block X, operand 2 in block Y, right? So that is the case. Then how you can do bitwise computing on that? So that means you have to bring those two operand or those two pages on a shared page, just like Ambit did. Ambit reserved a particular rows, right, for simultaneous activation. So similarly, we will reserve say block 0, right? This is our computing block. Now your data blocks, from the data block will fetch this operand using this same copy operation. And looks like a NAND already has this copy operation. So from data, from the array, the data will come to the buffer, and from buffer it will go to this logical page. So that is already a commodity command in NAND. So data movement inside the NAND without taking data out is already there. So we did that. We did this copy back operation. Second step, we'll write it on a shared word line together, and then we just do this shifted read. Then we shift the reference and read. If you do AND operation, shift low. If you want to do OR operation, will shift the other way. So that's the entire framework. So yeah, so that's pretty much I would like to conclude that you can do computation, bitwise computation inside the commodity chips with little bit modification in the either in the hardware or to some extent the memory commands. So if you're interested, I showed both the paper at the beginning for DRAM as well as flash. So in next class, maybe we'll look into analog computing inside the memory. Today's class was more like digital computing, bitwise. Next class we'll do multiply and accumulate, those kind of analog computing in the next class. Okay, so then we'll be ready with project topics. Okay, so I'll stop here unless you have questions.
So are we gonna start presenting our projects to you next week?
To me first. First you will.
Yeah, are we presenting it to you next week, or when is?
No, I think I'll still give you the date. I did not finalize it.
Oh,
yet,
okay,
but,
okay, cool.
I'll make an announcement. We'll give you at least a week.
Okay, cool.
Thumbs up. Yeah.
All right, perfect.
Thank you. I saw your.
Hey, Andrew.
I'll just follow you back to your office.
What do you think?
Cool, thank you.